Welcome to our video on clustering techniques in financial machine learning. I am Suryansh Mehrotra and with me is
Sandeepan Ghosh.
today we are going to walk you through the fundamentals of clustering techniques and their applications in finance and a comparison of popular methods. So let's dive in.
First, here's our agenda for today. We'll start with a quick overview of clustering and its importance in data analysis. Then, we'll explain some clustering techniques, including k-means, hierarchical clustering, and affinity propagation. Lastly, we'll provide you a comparison of these methods, highlighting where each is most useful. Let's begin with an overview of clustering itself.
So, clustering is a method of grouping data points so that those within the same group or cluster are more similar to each other than to those in other clusters. This technique helps us to uncover patterns within data that aren't always obvious. Common applications include market segmentation, social network analysis, and image segmentation. In clustering, we often refer to the terms like centroid, which represents the center of cluster, and unsupervised learning, meaning there is no labeled data. Instead, the algorithm discovers hidden structures on its own. This approach is valuable in scenarios where we don't have predefined categories or labels for our data.
So, let's start with clustering techniques. First, we have k-means clustering, one of the most widely used clustering methods. K-means is an unsupervised machine learning algorithm that groups data points into k distinct clusters based on their features. The main goal here is to minimize the distance between data points within each clusters while maximizing the distance between clusters. In k-means, the number of clusters k is a crucial parameter and must be decided beforehand. So, we'll now discuss about the process of k-means. To select the right number of clusters, we use methods like elbow method, where we plot the within cluster sum of squares WCSS and look for an elbow point where additional clusters provide diminishing returns. Another technique is the silhouette score, which measures how similar each point is to its cluster. Compared to other clusters, a higher score indicates better defined clusters. The process of k-means starts with choosing the number of clusters, k. Then the centroids are initialized by randomly selecting each data points. Each data point is assigned to the nearest centroid using a chosen distance metric like Euclidean or Manhattan distance. Afterward, the centroids are updated based on the assigned data points, and this process is repeated until convergence. As you can see, after that, we'll then evaluate the clustering results. Final clusters are reviewed and are then formed based on the centroids. This is the Python implementation of the clustering techniques. First, we will import the necessary libraries. We'll generate a sample data using random values. Then we'll initialize the k-means and then fit into the devised data. Then the plot results accordingly.
So next up is hierarchical clustering. So now let's look at hierarchical clustering, which builds a hierarchy of clusters forming a tree-like structures called a dendrogram. There are two types of hierarchical clustering. First is agglomerative, a bottom-up approach that merges the data points into clusters, and divisive, an up-down approach that splits clusters. So this technique is useful when we need a visual representation of data relationships or don't know the number of clusters ahead of time. We can cut the dendrogram at a certain height to get the desired number of clusters. So the process of agglomerative hierarchical clustering. So the agglomerative clustering process begins with each data point as its own cluster. Then the distance between clusters are calculated using metrics like Euclidean distance, and the two closest clusters are merged. This merging continues until we reach a single cluster or achieve the specified number of clusters. To update the distance matrix, we have options for linkage methods including single linkage, complete linkage, and average linkage. In single linkage, we choose the minimum distance points data points. In complete linkage, we choose the maximum distance data points, and in average, we take the distance of the both clusters. Finally, we create a dendrogram to visualize this hierarchy and cuts it at desired height to define the final cluster. We can see here the dendrogram, how it looks like, and the Python implementation. In Python implementation, we first import the required libraries, then we fit the model, define the model, then fit the model. You can see we have defined the number of clusters, and then we plot a diagram, as you can see.
Another powerful clustering technique is affinity propagation. Unlike k-means or hierarchical clustering, affinity propagation does not require specifying the number of clusters beforehand. Instead, it identifies exemplars, which are representative data points that define each cluster. This technique is great for discovering complex cluster shapes and for situations where the number of clusters is unknown. Affinity propagation is computationally efficient and performs well with non-metric similarities as well. The goal is to organize the data into meaningful clusters without specifying how many clusters there should be. This is the Python implementation. First, we will import the necessary libraries. We will create the affinity propagation and then fit it into the particular dataset. We'll then plot the results accordingly using scatter plot. Let's summarize these clustering techniques and see when to use which method. K-means is ideal for large datasets with a known number of clusters and when clusters are roughly in spherical in shape. Hierarchical clustering works best for small to medium datasets where visual hierarchy is needed and the number of clusters is unknown. Affinity propagation is suited for cases with complex cluster shapes, unknown clusters, and non-metric similarities.
Each method has its own strengths and fits specific data scenarios, so choosing the right one depends on your data size, structure, and requirements. So, to conclude, the clustering techniques are powerful tools in financial machine learning, enabling us to discover patterns and relationships within complex datasets, from k-means for well-defined large datasets to hierarchical clustering for smaller structured data and affinity propagation for flexibility. These methods open doors to deeper insights. Thank you all for listening. We are happy to take any questions in the comment section down below.